Okay, section 2.3 deals with mathematical modeling and the connection to functions. And it kind of covers different forms of mathematical modeling. Mostly what you're going to see is linear, which I'll talk a little bit about, and quadratic. Let's start with linear, just to review some facts from algebra. The idea of a linear equation is it has a slope, which is defined by rise over run, and that's our typical normal definition of rise over run. It also can be the change in y over the change in x. Also, we'll talk about the equation to find the slope of a line passing through 2 points, x sub 1, y sub 1, and x sub 2, y sub 2. And that is given by m is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Okay, so let's first start by looking at how to find the slope of a line passing through 2 points. So kind of going back to this formula, this is the main idea of a linear equation is, we have the slope formula and definition of slope. And we also have the y equals mx plus b, the slope-intercept formula. Okay. So, like I said, we'll do an example where we will find the slope of a line passing through the points 1, 1, and 4, 3, and we will make a sketch also of this line. So let me pull down the solution. Here. I think I'll just put them on the same page. So we will go to the slope formula, which is m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. If we plug those points in, it will be 3 minus 1 for your y values, and then second x coordinate is 4 minus first x coordinate is 1. Well, if we simplify that, 3 minus 1 is 2, 4 minus 1 is 3, so my slope is 2/3. And you can see the sketch. Here's the point 1, 1, we will go over 1, up 1. The point 4, 3 will be over 4, up 3. And, of course, that slope will be 2/3. Because, as you can see, the rise is 2 units and the run is 3 units. Okay. The next thing we'll do in a section, the book has these sections where you have to look at the equation and see if it's a linear form, and if so, then determine the slope and intercept. So let's do an example of that, where we have like I said, we have an equation, and what we're going to do is determine if it's linear. So determine whether the equation defines y as a linear function of x. If so, write it in the form y equals mx plus b. Okay, this is linear because notice that both the exponents of x and y are 1, so they're both degree 1. So that means that anytime you have x and y and no other exponents other than 1, it will be a linear function. So what we're going to do is take it and put it in slope-intercept form, or y equals mx plus b form. So in order to do that, we would have to get the x term over, so I'm going to subtract 2x. That'll result in negative 3y equals negative 2x plus 6. And then we can just divide through by negative 3. And that gives me, those cancel, we'll get y is 2/3 x minus 2. And that is our equation. What we've done is just rearrange the equation to the y equals mx plus b form. I'll leave it there for a second so you can copy it or pause. So let's look at an actual model then. a mathematical model that will be used to calculate some value. In this case, it will be a child's dosage. So Cowling rule is the method for calculating pediatric drug dosages. If A denotes the adult's age, then in milligrams, and T is the age of the child in years, then the child's dosage is given by, a typo, forgive me, that should be is. I'll have to go back and correct that. Is given by D of T, and notice it's in a function form, is T plus 1 over 24 times A. So, if the adult dosage is 500 milligrams, what should the 5-year-old child receive? Well, we would have to find D of 5. Notice T will be 5, and my adult dosage is 500 milligrams. So let's plug that in. It would be 5 plus 1 over 24 times 500 milligrams was A. Well, that will be 6 over 24. Let me write it in this unsimplified form first. Times 500 milligrams. So 6/24, which will reduce to 1 over 4. So if we take 1/4 of 500, basically, that will give me 125 milligrams of the drug that I want to. That is the dosage that we would give the child. And I have one more example. It's, again, just maybe a quick recap. All you have to do is really identify your two variables, which is T is the child's age, which is 5, A is the adult dosage, which is 500 milligrams, and it's a simple plug into the formula, which gives you 6 over 24 times 500, which will result in 125. Okay, one more modeling question. So more and more businesses and homeowners are installing solar panels on their roofs to draw energy from the sun's rays. According to the U.S. Department of Energy, the solar energy or solar cell kilowatt hour usage is projected to be S of T is 0.73 T squared plus 15.8 T plus 2.7. Let me write that down. That's our main model or function. A mathematical model, by the way, is just typically an equation or a function that you can plug in or manipulate to, find answers to particular questions. But basically, it's usually set up as an equation that you can plug the values in and, project, whatever they're asking for. Okay, in year T, let me finish the question. I think I have another typo. Just get rid of the with. So with T equal to 0 corresponding to the year 2000, what is the projected solar cell kilowatt hours used? Projected solar cell kilowatt hours used in the U.S. for 2003 and 2007. So in 2003, we're going to use T is 3. So that would be, and I may have to go to another page. I think I will. I'm just going to do 3 for right now. So we're going to find S of 3, which represents 2003, which will be 7.73 times 3 squared plus 15.8 times 3 plus 2.7. And I'll get my calculator here. I'll see how that works out. So we're just plugging in 3 basically. So 3 squared is 9, by the way. And then 58.3 or 15.8 times 3 is what I meant to say. It's 47.4 plus 2.7. And I'm just going to run the rest of that in one line on the calculator. I think most of you can handle this substitution. It's not a big deal. And it comes out to, I'm going to round up to, it's 56.67. I'll round up to 56.7 kilowatt hours used. Okay, let's do for 2000, I'll just write on the paper down here. For 2007, we'll use S is 7. So that would be 0.73 times 7 squared plus 15.8 times 7 plus 2.7. And that results in about 149 kilowatt hours. Oh, and by the way, that is, let me reiterate, that is actually 0, my mistake, 0 kilowatt hours. That actually represents that's what seemed, this was actually in, I believe, thousands. So I left that out of the problem. So let me pause just for a second. Okay, that should have been in millions. So what we can do is, actually we can just, I thought it'd be easier rather than redoing the whole video. I made the typo correction. As you can see, I pulled up my PowerPoint slide. And it is in millions. And then now if we go back to the solutions, those will both be in millions. That sounded a little bit low, but basically it comes out to basically 56.7 million. You're probably thinking, wow, that seems really low, like ultra low, and it was ultra low. So that seems more practical for the whole U.S., you know, in terms of solar cell usage. And then in 2007, it increased to almost 150 million kilowatt hours that were used. Okay, so that wraps up our unit on functions and modeling. Please continue to, work problems out of the TAM book and on WebAssign. But again, hopefully we could just make the correction right there rather than redo the whole video. I think that this makes things easier. Thanks for your time.